Okay, this video is about the material in Chapter 8, which pertains to large sample theory. Okay, so what are the goals of large sample theory? Well, up until this time, we've been deriving all the properties of the estimators, assuming that the regressors are non-stochastic, so the x's are fixed, and assuming that epsilon is normally distributed. Okay, but we would like our results to apply more generally, like to not have to assume those strong assumptions, okay? And we can actually derive the properties of the OLS estimator, allowing for random x's and allowing for the epsilon to be non-normally distributed. Okay, so that's kind of what we're going to do with large sample theory is we're going to derive out properties of estimators under more general assumptions. And what types of properties would we be interested in? So usually the properties that people want to show is consistency. Does the estimator approach the true value as n gets large? Asymptotic normality. What is the limiting distribution? So this is something we would need if we want to do any sorts of tests. And asymptotic efficiency is whether this estimator has the lowest variance within its class. Okay, we're not going to talk a lot in this class about how you prove asymptotic efficiency, but I'll just mention that the OLS estimator is efficient. It actually has this property called BLUE, which is it's the best linear unbiased estimator. So within the class of linear estimators, it has the minimum variance. Okay, but we're not going to show it because the proof is a little bit more involved in terms of using matrix algebra than what I wanted you to do for the class. Okay, we're going to study 4 different notions of convergence. So what does it mean to say something converges to something? Well, if an estimator approaches some value as the sample size gets large, then that estimator converges to that value. Okay, so for example, suppose we have like a sequence of random variables, and then suppose that, let's see, xn is, okay, well, this would be xn is the sample mean of y. So y is, say, the data, and then xn would be taking the mean of the data up through n. And so as n gets large, you're taking the mean over and more observations. Okay, so we would say that xn converges in probability to x. Okay, so x in this case is going to be the population mean of y. This is the sample mean, and this would converge to the population mean. So xn converges in probability. So this is the first notion of convergence in probability. If this is true, okay, so that means that as n gets large, the probability that xn differs from x by more than epsilon is equal to 0, or equivalently, you can say the probability that xn is close to x in terms of being less than epsilon equals 1. So for any small epsilon, for large enough n, the probability that the distance between xn and x is greater than epsilon would equal 0. Probability it's less than epsilon equals 1. Okay, so these are equivalent. You can write it either way. Okay, xn converges in mean square to x. So this is a different notion of convergence. And this is the definition of convergence in mean square. Okay, when x is the mean of xn, then this is the same as showing the variance goes to 0. Okay, I'll talk a little later about the relationship between the different modes of convergence. Okay, so this is a third notion of convergence called almost sure convergence. But in class, we're not really going to use this because for most of what we do, the first one and the second one are sufficient. Okay, almost sure convergence is actually called strong convergence because this is a stronger notion of convergence than convergence in probability. Okay, this says as n gets large, the probability that xm is different from x is less than epsilon for all m greater than or equal to n. So this means that xm gets close to x and then it stays close. Okay, like if you compare it with convergence in probability, this just says, it gets close in a probability sense, but it doesn't imply that it stays close. So this is a stronger, almost sure convergence implies convergence in probability. This is stronger. All right, and then the last notion of convergence is convergence in distribution. And this is the weakest notion of convergence. If we say that xn converges in distribution, that just means that the distribution of xn converges to the distribution of x. So it doesn't mean that the x's are normally, or that x's are close. It just means, let's say the distribution of x is normal, then it says in the limit the distribution of xn is normal. So we're not saying the x's themselves are close, we're just saying that they'll have the same distribution. Okay, xn will have the same distribution. All right, so actually there is a relationship between these different notions of convergence. And the relationship is that convergence in mean square implies convergence in probability. Also, convergence almost surely implies convergence in probability. Okay, so mean square and almost sure convergence are stronger than convergence in probability. And then all mean square in probability convergence and almost sure convergence all imply convergence in distribution. Okay, so the first three implies the fourth one. So if I wanted to show convergence in probability, I could either show that directly, like using this definition, or I could show convergence in mean square and then use the fact that mean square convergence implies convergence in probability. Okay. All right, let's look at an example. Okay. So this example is going to show that xn converges in probability to 0, but that it does not converge in mean square. Okay, so remember, mean square convergence implies convergence in probability, but not vice versa. Okay, so this random variable, it equals 0 with this probability, 1 minus 1 over n, and it equals n with probability 1 over n. Okay, so now let's look and prove that it converges in probability. So what's the probability that xn deviates from 0? Okay, well, the only time it's different from 0 is here. Okay, so the probability of that happening, so here, the probability that this is less than epsilon, so that would be all these cases. You can see in the limit that this goes to 1. Alternatively, you could have written what's the probability it's greater than epsilon, which is 1 over n, which goes to 0. Okay, so you could do it either way. Now let's analyze whether it converges in mean square to 0. Okay, so for that we have to look at e of xn squared minus 0 squared. Okay, and this equals n, so this is not going to 0. So if you look back at convergence in mean square, this is what you have to show. Okay, so this tells you that this converges in probability to 0, but it does not converge in mean square to 0. Okay, these are the relationship between the different notions of convergence that I was just mentioning. So almost sure implies convergence in probability. Mean square implies convergence in probability, and convergence in probability implies convergence in distribution. Okay. Actually, I can make the screen slightly bigger. Now let's look at some useful theorems. And these are theorems we're going to apply when we show asymptotic distribution of different estimators. Okay, first Slutsky's theorem. If xn converges in distribution to x, and an converges in probability to a, then if I multiply an times xn, that converges in distribution to a times x. Okay, if I add them together, that converges in distribution to a plus x. And if I divide them, it converges in distribution to x divided by a. Because we're going to deal with estimators that are like things multiplied together or divided by each other, you know. Okay. Now the second theorem we're going to invoke sometimes is called well, it actually has two names. It's called Man-Wald theorem, or some people call it the continuous mapping theorem. Okay, and the way I remember it is this little phrase here: the p-lim of a continuous function is the continuous function of the p-lim. And it basically says if I have xn converging in distribution to x, and g is a continuous function, then g of xn converges in distribution to g of x. Okay, and the same is true for convergence in probability or convergence almost surely. Okay, so this is very convenient because sometimes we'll have expressions and it'll be like some function of that expression. So, like for example, we'll have like x prime x inverse, you know, that'll be like a function. Okay, now laws of large numbers. So laws of large numbers are basically applied to averages. And it basically shows that when you average a bunch of variables, as n gets large, the randomness goes away. So there's actually many different laws of large numbers. There's some books, like there's a book by Hal White that the whole book is like laws of large numbers and central limit theorems. It's we're just going to use a couple, or actually just one law of large numbers and one central limit theorem. So, and it's called Chebyshev's weak law of large numbers. So the key assumptions, so if I have some yi, and they have a finite mean, you know, some given mean, some given variance, also finite variance, then the average of the y's converges in probability to the mean. Okay. Now, weak consistency is basically saying, well, this is, you apply the law of large numbers, and that's, you know, can be used to show weak consistency. So if I have some estimator, you know, if it converges in probability to mu y, like mu hat y converges in probability to mu y, then we would say it's weakly consistent, okay? But we're going to be applying laws of large numbers to establish weak consistency. Okay. There's also law of large numbers, which are strong laws of large numbers, and they imply almost sure convergence. But we're just not going to deal in this class with almost sure convergence. But I'll just tell you that there are, you know, other laws of large numbers. There's some that like relax some of these assumptions, you know. So, but I mean, most of what we're going to deal with, actually, these assumptions are okay. So we'll just kind of use the standard conventional method. Okay. Now, so we did, you know, these are all the tools we're going to need. So Slutsky theorem, continuous mapping theorem, law of large numbers. So this is going to be used to show that things converge in probability. Almost always it's going to be to show a mean converges in probability. Now, asymptotic normality. So remember, before I assumed that epsilon was normal, but we'd like our results to apply more generally. And it turns out that you can get normality from a central limit theorem. So even if the underlying epsilons are not normal, you know, you can you can derive that the OLS estimator is still normally distributed. Okay, so it's going to generalize our results because it's going to apply for regressions for any distribution of epsilon. It doesn't have to be normal. Okay, let's look at the central limit theorem. So if we have a sequence of IID random variables and we consider the sample mean, okay, and the expectation of the mean is this, and the variance of the mean will be this, right? Because it'll be like 1 over n squared times n times the variance of x. So it's sigma squared over n. Then if I take the mean minus the expectation here, mu, divided by the square root of the variance, and call that z, by the central limit theorem, z will be normally distributed, mean 0, variance 1. Okay, this object. Okay, and this is the Lindbergh-Levy central limit theorem. Okay, so what makes it that central limit theorem? Well, it's invoking these assumptions with some mean and some variance. So there are central limit theorems that would allow the variance to depend on I. You know, not assume that they all have the same variance. So there are some more general central limit theorems, but we'll just go over this one. I don't want to, present. If you took a more advanced class in asymptotics, you'd probably cover a lot more central limit theorems. But this is one that's commonly applied, so we'll just do this one. Okay, so these are just exercises from the back of the book. So if you want to do this exercise, it's basically you just do exactly what we did here. So just write down, let's see here. You would just do exactly what we did here, but just with a different expression here. All right, and then let's see. Yeah, so these are just exercises at the back of the book. This one, well, this one, you have to use if you divide by n minus k divided by n minus k, remember we derived out some results about 1 over n minus k times the sum of epsilon I hat squared, that the expectation of that was sigma squared, right? So if I pre-multiply by n minus k divided by n minus k, that helps in analyzing this p-lim. Okay, and now here, here we would be applying, like Slutsky's theorem and Manuel theorem. So we have delta hat, convergence in probability, theta hat, convergence in probability, theta naught. So the ratio converges in probability to delta naught divided by theta naught by the Manuel theorem, or continuous mapping theorem. And then this converges in distribution to, let's see, gamma naught. And so then by Slutsky's theorem, because this is distribution, this is convergence in probability, then by Slutsky's theorem, the overall thing is going to converge in distribution to delta naught divided by theta naught times gamma naught. Okay. All right, so you just have to apply continuous mapping theorem to this ratio and then apply Slutsky's theorem to these two things multiplied together. Okay, so that completes right now this chapter is basically just introducing these various things, and they're really going to be used in the next chapter when we analyze the distribution theory for the OLS estimator using these theorems like central limit theorem, law of large numbers, Manuel theorem, and the Slutsky's theorem. So we're going to use all those things in chapter 9.